For this learning plan, we are looking at parts of Chapter 9 and of Chapter 20. So far, we've looked at a few of the hardest working components in our PCs, the processor and memory. But these components would have little to do if they didn't have data to work with. A little later, we'll look at where that data originates. But now we're going to look at how data gets to the RAM and the processor. Data transfer occurs over wires, either in data cables or trace lines on a circuit board. It can also occur wirelessly, but that's a topic for later. These wires might be connected to a peripheral device and your system case via a port and connector, or to an internal component and your system's motherboard via connectors and connection points. In PCs, we use the term bus to identify these different wires. Think of a bus as the electronic highway on which data travels within a computer from one location to another. Basically, it's the conduit used by your entire system to communicate with your processor. When used in reference to personal computers, the term bus usually refers to what is commonly called the local bus or the system bus. This is the main bus on the electronic highway, and we've seen that it connects the processor to the main memory on the motherboard. The size of a bus, known as its width, is important because it determines how much data can be transmitted at one time. The bus size actually indicates the number of wires in the bus. So for example, a 32-bit bus has 32 wires or connectors that transmit 32 bits simultaneously, which is parallel data transfer. It would be considered 32 bits wide. A 64-bit bus has 64 wires or connectors that can transmit 64 bits of data in parallel. All buses consist of two parts, the data bus and an address bus. The address bus is the set of lines that carries information about where in memory the data is to be transferred to or from. No actual data is carried on this bus. Rather, it carries memory addresses, which control the location that the data is either read from or written to. The address bus is used to identify particular locations or addresses in main memory. The width of the address bus, that is, the number of wires, determines how many unique memory locations can be addressed. Modern PCs and Macs have as many as 36 address lines, which enables them theoretically to access 64 gigabytes of main memory. However, the actual amount of memory that can be accessed is usually much less than this theoretical limit due to chipset and motherboard limitations. The speed of the address bus is the same as the speed of the data bus that it is matched to. The address bus is typically represented as connecting directly from the processor to the RAM. It is a one-way bus because only addresses travel on it, not data, as just mentioned. Just remember that it also extends alongside every other bus to carry those memory address locations to each component and device. From the beginning, computer buses on the motherboard were parallel buses, sending data down more than one lane simultaneously. The width of the bus depended on how many lanes or wires were in the bus. Each wire can transport a single bit of data, and we had 8-bit buses, 16-bit, 32-bit, and 64-bit buses. Now there are motherboards with 128-bit memory address buses to take advantage of dual-channel RAM. Data on buses does not all travel at the same speed. The speed of the front side or system bus is controlled by the same chip that controls the timing for the processor, your system crystal. The front side bus doesn't move as quickly as the processor does, but it's getting closer. Initially, early expansion slots had their speed controlled by a crystal on the motherboard specifically for this task, called the expansion bus crystal. Data on the expansion bus does not move as fast as on the front side or system bus. The expansion bus is an asynchronous bus, meaning that it does not run in step with the system clock. Even today, there are devices in your computer whose timing is controlled by the separate, slower expansion bus crystal and not the main system crystal. The first slots widely used on the expansion bus came to be known as Industry Standard Architecture slots, or ISA slots. Initially, their data path was 8 bits wide, so they were known as 8-bit ISA. To speed things up, a 16-bit ISA bus was soon in use. The cards and slots connected to this bus controlled functionality for everything in the system, from video cards and monitors to sound cards and speakers, as well as input-output cards with connections for hard drives, floppy drives, serial and parallel ports. And remember, at this point we were in a DOS world with DOS applications, which meant little or no color and no graphics. So ISA was quite adequate for this. Next came the 32-bit expansion buses. First was MCA, Microchannel Architecture. This was a proprietary bus developed by IBM, and it was not compatible with ISA. It was a 32-bit bus. It doubled the pathway and increased the speed. But it was proprietary, which meant that any manufacturer who wanted to use this bus on their motherboards had to pay IBM for the privilege. So the other manufacturers got together and developed their own non-proprietary bus that anyone could use. They called it Extended ISA, or EISA, which is spelled EISA. This was also a faster 32-bit bus, but it was not interchangeable with MCA. It was, however, backward compatible with ISA, so you could still use your older ISA cards as well as newer EISA cards in your system. This essentially knocked MCA out of the race, and things were fine for a while. Then Microsoft came out with Windows. The 32-bit EISA or MCA video cards just didn't work fast enough for the color and graphical demands of Windows. They were still run by the asynchronous expansion bus crystal. So, on 486 processor systems, we saw the widespread use of a new bus called the VISA Local Bus. This bus was not run by the expansion bus crystal, but tied into and ran at half of the speed of the front side bus speed, which made it a local bus. It was also 32 bits wide, but it was based in part on the slow ISA architecture, and it didn't last beyond the 486 generation systems. When Pentium systems were being developed, Intel realized that a faster bus for expansion cards would be needed, so they developed the PCI architecture. This was also a 32-bit bus, but it connected directly to the front side or system bus running at half or a quarter of that speed. The architecture was completely reworked to increase efficiency and throughput. It transfers data at 264 megabytes per second, very useful for Windows 95, 98, and ME. And unlike many previous expansion bus types, it functions independently of any particular type of processor. On early Pentium systems, you saw ISA slots along with PCI slots. The ISA were used for older devices where performance was not as big an issue. PCI was used at first just for video, then for network and sound cards. Once again, however, advances in software drove the need for better hardware, primarily because of gaming and video needs. Accelerated Graphics Port, or AGP, slots and cards were developed. These were also generally 32-bit and directly connected to the North Bridge and the system bus. Because they were dedicated to video, that was the only data traffic on the bus, they could be faster than PCI, reaching speeds up to 528 megabytes per second, and they could run at the complete speed of the system bus. PCI-X is a backward serial compatible bus that improves the speed of traditional PCI to increase performance for high bandwidth devices like Gigabit Ethernet and Fiber Channel. These are found mainly on server motherboards. Mini PCI is a small card that uses less power and can lie flat. This makes it ideal for use in laptops, and we'll talk more about Mini PCI when we look at laptops. These buses all use parallel data transfer, moving more than one bit at a time, side by side, across a wider bus. Now, there are some limitations inherent in this technology. With parallel data transfer, once you reach a certain speed, you run the risk that your data won't all arrive at the destination at the same time, and a delay of even a micromillisecond means corrupted data, or else another delay for reassembling the data in the proper form and order. But serial transfer, especially when data is sent in packets, gets around this limitation. And some data doesn't require a great deal of bandwidth in order to be sent serially. PCI Express is the newest bus being used in desktop systems. It's still PCI technology, but instead of transferring data in parallel, it is a two-way single file connection that carries data in packets along pairs of data lines. This transfer is faster than parallel because each PCI Express slot has its own connection to the frontside bus instead of sharing the connection with other PCI slots. PCIe uses one wire for sending and one for receiving. These pairs are called a lane. Each lane runs at 2.5 gigabits or 5 gigabits per second for PCIe version 2. And PCIe can use one or more lanes for different devices, anywhere from 1 to 32. Each lane moves data independently of the others. The most common is 16 lanes for video cards. PCIe by 16 slots also connect to the bus through the North Bridge. In the case of motherboards with two PCIe by 16 slots for two video cards, they will each have their own connection to the North Bridge. Other devices don't need that amount of fast data transfer, and they connect to the slower end of the system bus through the South Bridge chip. Now let's see how these things look. Devices that connect to the motherboard on expansion card must be on cards that fit into specific slots. As improvements have been made, these slots have changed in size, data path or bus size, and speed. So expansion slots are differentiated by color, size, number of pins, and offset. Take a look at the Lab 8 reference document. ISA slots are traditionally black or dark brown. They have relatively few pins and the pins themselves are wide. They have either one or two groups of pins depending on whether they're 8-bit or 16-bit ISA slots. The offset is the distance from the edge of the motherboard to the start of the slot. There is a corresponding offset on the card. For ISA slots, this offset is small, about an inch. Some slightly older motherboards may still have one ISA slot for backward compatibility. VESA slots are the same as ISA slots with an extra lighter brown slot at the inside end. The offset is the same as the ISA slot. VESA slots are the longest slot. You will not see these on current systems, but you will find them on 486 generation motherboards. PCI slots are white or off-white. These have close-set, thinner pins. The offset is about 1.5 inches from the edge of the motherboard. The slots themselves are about 4 inches long with pins in two groupings, a larger group, then quite a small group. There may be anywhere from 3 to 6 of these on a motherboard. AGP slots are usually brown. These are the same size as PCI slots, but the offset is more than 2 inches from the edge of the board. The groupings of pins have a small group first, then a larger group, and the pins themselves appear to be staggered on the card. There would be only one of these on motherboards that use them. PCI Express slots come in different sizes. Some are quite short, others half the size of regular PCI, and some the same size, but they are usually darker in color, such as black, or white, like the original PCI. The offset is closer in length to that of PCI, so it's shorter than the AGP offset. When data needs to come into the system from the outside, such as from a keyboard or a printer, scanner, or a webcam, it must be transferred from that device through a port located directly on the motherboard or on an expansion card. Over the lifetime of PCs, there have been several different types of ports, each with different methods and speeds of data transfer through them. Take a look at the Lab 12 reference document. These are the connectors and ports commonly found on system cases, peripheral components, and cables. Some of the data in your system comes through ports on expansion cards or directly on the motherboard as onboard or integrated ports. It's cheaper to have onboard ports, but it can make adding a device or upgrading one a little more complicated. In early systems, the only onboard port was the keyboard port. All other devices you wanted to connect required that an expansion card be installed into a slot on the motherboard. This card contained the port to which you connected your device, whether that was a floppy drive, because remember, the very first PCs had no other drives, such as hard drives, a printer, your monitor, or a modem. The very first input-output port on PCs transmitted data into the system in serial order, one bit following another and using one wire to send data and one wire to receive it. Appropriately enough, it was named the serial port. Many devices use serial transmission. Keyboards, mice, and modems, for instance, use this type of transfer regardless of how they typically connect to this system. The ports on your case that are traditional serial ports are the serial or COM ports, the PS2 keyboard and mouse ports, and on very old systems, the DIN or AT keyboard port. Notice that all of these have more than 2 pins or holes, so what are these extra wires and connections for? Not only data has to be transferred through the system, memory addresses and control signals also accompany data to and through the motherboard, and your keyboard and mouse are powered this way as well. This is why the serial port has 9 pins and wires. Devices that initially connected to the serial port were the earliest dot matrix printers and external dial-up modems. The mouse began to be used when Windows 3X came out, and this also connected to the serial port at first. The serial port was responsible for taking that serial data coming in and converting it into parallel format so that it can move across the buses on the motherboard. The part of the chip that handles this conversion is a chip called the UART chip, or the Universal Asynchronous Receiver Transmitter chip. Today, even if your PC does not have physical serial ports on the back, you probably still have COM ports in your system. Now, what's the difference between serial ports and COM ports? Are they the same thing? Well, serial port is a name for the physical port on your PC. COM port is the designation for the logical port, the way your system BIOS and your operating system see or identify a physical device. Devices like internal modems, which receive and transmit data in serial, contain their own built-in UART chip to perform this serial to parallel conversion of incoming data, and then parallel to serial conversion for outgoing data. Even if a modem were to be built into the motherboard as an onboard port, there will be a UART chip on the motherboard to take care of this conversion. The situation was a bit different for keyboards. Keyboards only transmit 1 byte of data at a time, in other words 8 bits, and the speed at which information is typed affects how fast this data moves into the system. Even the fastest typist can't press the keys fast enough to overwhelm serial data transfer. The AT keyboard port needed only 5 wires to do its work. IBM redesigned this port for the PS2 computer and added an extra pin and wire for control signals to make it a 6-pin connector and port for keyboards, and then added another one for the mouse once that was here to stay. Obviously, serial ports for devices other than keyboards and mice couldn't keep up as systems got faster and data got more complex. The 2 ports that came next were 25-pin parallel ports for printers and 15-pin ports for monitors and video cards. Both changed from serial transfer across their cables to parallel transfer. In parallel transfer, a whole byte of data can be transmitted at one time, 8 bits going side by side. Compared to original serial transfer, parallel is pretty fast, especially if you're only dealing with a few colors on monitors and minimal graphics on the screen or being printed. Even as data got more complex, these ports were adequate for a long time and have only recently been replaced. For video, the 15-pin VGA port has gone through several functional updates, although its appearance hasn't changed. The VGA port moves analog data, but we're seeing an increase in moving digital video data, so the new DVI ports are showing up on video cards, monitors, and video cables. For most other devices, we are now using USB for faster transfer, which just happens to be serial again. With the Universal Serial Bus, designers found a way to move that single file data more quickly than the old serial transmissions and faster than current parallel transmissions. Bits are grouped into packets and pushed across the wires in short, speedy bursts. Today, keyboards, mice, printers, modems, and other devices can connect to the USB ports. The computer has an integrated circuit built into the chipset called the USB host controller. Inside this controller is the USB root hub, which makes the physical connection to the installed USB ports. This divides up the bandwidth available on this bus, so every USB device shares the bus with other devices connected to the same USB root hub. The more devices connected to the same host, the slower they will all be. And since some USB devices draw their power through the bus as well instead of being externally powered, you could run into power issues with too many USB devices as well. You can get around this by using powered USB devices and connecting some devices to powered hubs. USB will still be faster than the serial or parallel ports that they've replaced. There are several different speeds that USB can operate at. The earliest USB release had two speeds, low speed at 1.5 megabits per second and full speed at 12 megabits per second. The USB 2 standard introduced high speed USB running at 480 megabits per second. USB 3 was released early in 2010. It's called Super Speed and runs up to 5 gigabits per second. It also increases power to peripherals and has full backward compatibility with older USB devices. You can plug a lower speed device into a high speed or super speed port, but they will run at their slower speed. USB host controllers support up to 127 devices, but most systems come with far fewer than 20 actual USB ports. If you want to connect more, you can use a USB hub. Be aware, though, that cable length presents a limitation to USB data transfer. USB cables can be no longer than 5 meters. If you need more distance, you'll want to connect these devices to hubs and then connect the hubs to system ports. USB is plug and play and hot swappable, but that doesn't mean that there can't be problems. You should always install the driver for a newer USB device before you connect the device. Even if Windows has basic drivers for your device, it's worth installing the driver that came with the device in order to get its full functionality. Another new serial transfer is IEEE 1394, more commonly referred to as FireWire. FireWire is very similar to USB transfer. The main differences are that IEEE 1394 is meant to be used mostly for devices working with a lot more data than USB devices like camcorders, DVDs, and digital audio devices. Secondly, where USB can chain up to 127 devices, FireWire can only connect 63. And third, USB is controlled by a host controller, but FireWire is peer-to-peer. two devices can talk to each other directly over the bus without going through the PC's bus systems. Speed-wise, FireWire A runs at 400 megabits per second and FireWire B at 800 megabits per second. USB and IEEE 1394 are used for external devices that connect to the system bus through either expansion cards or through onboard ports. With all of these ports, be aware that they will show up in Device Manager if they are present in your system. And if they show up there, they can also be disabled from there. This is an area to check if you are having problems with any port or device. Also, since we use USB ports in particular for so many devices, the ports themselves can sustain some damage over time and stop working. It's best to be gentle when attaching USB devices or plugging in and removing your flash drives. This concludes our discussion of expansion slots, ports, and connectors.